So, as the title of my talk says, I'll be talking about monotone Lagrangians in cotangent bundles, and from very early on, I'll specialize to the case of T star of S3, the cotangent bundle of the 3-sphere, but at least some of the things that I'll say should have analogs to other cotangent bundles, and we can talk more about that later if you'd like. So this is joint work in progress with Mohammed Abouzaid, and I'll begin by here's a brief outline of what I'll talk about. So I'll begin by just have a quick motivation to the problem and statement of the main theorem, and then I'll tell you something about the monotone wrapped Fukaya category, then formality and classification of modules, and then Lagrangians at the end. We'll go back from the algebra to the geometry of Lagrangian in this cotangent bundle. So what I want to, the idea I want to convey is, first I'll motivate the problem and state the theorem, and then what I want to do with the rest of the hour is to actually try to give you an idea of what's like the skeleton of the proof, what makes the argument work, and what makes the argument work is mostly algebra, so I'll try to. So a lot of the statements that I'll make and a lot of the claims that I'll make will be a little bit abstract. I'll be talking about, if you haven't heard of these things, I'll be talking about certain Lagrangians generating, certain objects generating categories. I'll be talking about categories of modules. And I will not be defining all these terms, but hopefully the statements themselves carry some intuition, and I'll try to also give some motivation for what those more algebraic statements mean. So I understand that if what I want is to capture your attention, maybe this is the wrong thing to say at the very beginning, but there's going to be a lot of algebra on the board, but I'll try to do my best to illustrate to try to give an idea of what all these statements mean. So okay, so we start with so we'll be talking about Lagrangians in cotangent bundles. So let's just recall that we have if n is a closed manifold, then we can take its cotangent bundle T star M that has a symplectic form that's exact, where lambda is just the one form PDQ. Cotangent bundle of n, and I'll be mostly interested in n, the 3-sphere. So that will be my main focus. So I'm interested in Lagrangians in cotangent bundles. So the first Lagrangians, the simplest Lagrangians to consider are exact Lagrangians. So L inside T star n Lagrangian is exact if this one form whose derivative is omega, if lambda restricted to the Lagrangian, so this is a one form on the Lagrangian, this itself is exact. It's the derivative of some function, okay? And exact Lagrangians are particularly nice. There's not supposed to be that many exact Lagrangians in cotangent bundles. So there's this Arnold nearby Lagrangian conjecture that says that if you have a closed exact Lagrangian on a cotangent bundle, then you expect it to be Hamiltonian isotopic to the zero section. Okay, and so this is as far as I can tell, far from being settled. It's known in some cases like S2, I guess more recently T2. There's some results. There's a lot of results that ended up culminating in this theorem of Abouzaid and Thomas Krag that says that if you have one of these exact Lagrangians, then if you take the map, the inclusion map, and you compose it with projection onto the 0 section n, then this map from L to n is actually a simple homotopy equivalence. But the nearby Lagrangian conjecture is still a very hard open problem. So what we're going to do is, because it's a very hard problem, we're going to consider possibly harder classification problem. We're going to allow more Lagrangians, and we're going to see what we can say about trying to classify in some very weak sense, maybe a wider class of Lagrangians on cotangent bundles. So I'm going to, instead of just consider exact Lagrangians, I'm going to consider monotone Lagrangians. So L inside T star n is monotone. I should say non-negative monotone if there is a non-negative constant tau such that what happens? So for every map U from the disk to the cotangent bundle, taking the boundary of the disk to the Lagrangian, so we have a map from the disk to the cotangent bundle. I can take the integral of omega along this map. So this is telling you what the area of the curve is, of the map U is. So this is supposed to be tau, the constant, times some number mu of U, which is the Maslov number. Which I'm not really going to define. Let me just say very vaguely. Most of you are very familiar with this. So U is a map from the disk to the cotangent bundle. The boundary is a map from the boundary of the disk. So this U sends the S1 boundary to the Lagrangian. And so as I move along this path on the Lagrangian, I have, so for every point in the Lagrangian, I have the tangent space to the Lagrangian. That's a Lagrangian subspace of the tangent space to the cotangent bundle at that point. So what I have is, I can think of this map as defining a loop of Lagrangian subspaces of this cotangent bundle, and this Maslov index is measuring, in some sense, how much this path of Lagrangian, this loop of Lagrangians rotates, and this is a nice condition because it's saying that how much this Maslov number, this Maslov index, is a multiple of the area of the curve, and so this Maslov number is important because it shows up in dimension formulas for moduli spaces of disks, which are the ingredients in Floer theory, and so this is saying that if we're trying to count rigid configurations of disks in some sense, then we should look for disks with a low dimension, so low Maslov number. So disks that appear in moduli spaces of low dimension, which means low Maslov number, which means low energy. So in this monotone case, we can really, just to do Floer theory, it's enough to restrict our attention to disks of low area, which is very useful for technical purposes. And so what I want to do is to study these monotone Lagrangians in T star of S3. So the goal is to study monotone L in T star of S3 using Floer theory.
Does this number have to be even? Can it be anything?
Which number? Mu? Well, if the Lagrangian is orientable, then yes.
Okay.
All right. So any other questions?
Can you give us examples for monotone?
Yes. Thank you for asking. That was the next thing I wanted to say. So let me give you some examples of monotone Lagrangians in T star of S3. So it's going to be useful to think about T star of S3 from the point of view of Lefschetz vibrations. So I'm not going to go into the details of that, but T star of S3 is symplectomorphic to the affine complex quadric, re-quadric, the affine complex quadric threefold. So this is the total space of what's called this A2 this A2 Milnor fiber, this Lefschetz vibration that looks like this. So even if you haven't thought about this, if you haven't seen this, what happens is that there's a map from T star of S3, thought of as this affine quadric, to C. And this map, so there's going to be two critical values here in C, and then over each of these critical values, I'm going to have certain critical fibers. And then if I take some value that's not if I take some point that's not a critical value, that's a regular value, then what happens is that the fiber over this point is a copy of T star of S2. Here is my S2. And then what happens is that when you get closer to these critical fibers, these S2s vanish to points. These S2s are vanishing, what's called vanishing cycles. So over the critical fibers look like these nodal configurations, these singular varieties. And then what we're going to do is, our goal is to try to define some monotone Lagrangians in T star of S3. So let me give you a way of doing that. So if I take a path here, so this is the base C. If I take a path gamma here, then this path gamma lifts. If it's a path gamma that goes around the two singularities, then you see over each point, I have a smooth fiber. Okay, and so on that smooth fiber, I have my vanishing cycle, my Lagrangian sphere on the fiber, and then I can just take the union of all those, and what I get is this Lagrangian that looks like S1, the base S1 times the fiber S2. Okay, are these colors okay? All right. So, and then what happens is that if I take, I'm not going to make this picture more crowded, but what happens is that, so you see there's this path here in the base. It bounds a certain area. Let me call this area A. And then this guy, this Lagrangian, S1 times S2, as it turns out, is going to be monotone for some tau that is, if I got it right, equal to A over 2. Okay, so you can think what you can think of doing now is of you have these two critical points. Take the two critical values. Take a segment connecting them. Actually, if you think about what is a Lagrangian that lives over this segment, it's actually the zero section S3. And then what you can do is you can exhaust the complement by closed curves, disjoint closed curves of increasing area. And what this gives us is a family, a one-parameter family of monotone S1 times S2s with increasing monotonicity constant. Okay, so what we have here is a construction of a one-parameter family of monotone S1 times S2s in T star of S3. Okay, so this is one example. And okay, any questions about this example?
Is it topological trivial S1 plus S2? Is there a possibility of you get some S3 or some?
Yeah, in principle, this bundle might not be trivial. This bundle over S1, but it is in this case. Yeah, because basically, yeah, it's like, yeah.
Is there any reason?
So what to say? The reason is, I mean, there's some choices here to be made, and like, so this you can think of this the construction of this Lagrangian as follows. So you can write down some symplectic structure on this total space of the Lefschetz vibration with that has a certain this induces a symplectic connection on this vibration, and then you can set things up in such a way that when you take here over a point, you take a sphere, and then you think about the parallel transport of that sphere along this loop, and you can set things up in such a way that this actually closes up. You come back, you come back to the exact same sphere, and the monodromy is the identity. But this is, I would say, it's a feature. There's some choices to be made here that I haven't specified, and under those choices you can achieve this. Yes.
So a priori there are two sort of obvious symplectic forms here. The exact form on the Liouville form on T star S3 and the one from the affine embedding as a quadrant. Are they the same?
Well, so this is these two are symplectomorphic.
Right, but in some very explicit fashion.
Right.
I mean,
You can write this. You can write down an explicit symplectomorphism between T star of S3 with the. Yeah. All right. So what we're going to do is I don't want to spend too much time on that, but there's a similar picture for T star of S3. So this is I learned about this from a paper by Chan, Pomerliano, and Ueda. And so what they do is they describe T star of S3 not as a Lefschetz vibration over C, but as what you could call a Morse-Bott Lefschetz vibration. So it's a picture similar to this one, but the fibers, instead of being T star of S2s, the smooth fibers are T stars of T2s. Okay, so similar. There's a similar Morse-Bott Lefschetz vibration from T star of S3 to C, such that the smooth fibers are T star of T2, okay? And then you see, if you do a similar picture of taking this, these T2s around a loop for a ride, then these lifts of loops on the base, still this I haven't said, but this Morse-Bott Lefschetz vibration also has base C and also has two critical points in the base. Okay, so if you again take a loop that goes around the two critical points and you lift it to a Lagrangian, this Lagrangian is going to be of the form S1 times T2, so it's going to be a Lagrangian T3. Again, it's going to be topologically trivial. So loops in the base, loops gamma in the base lift to Lagrangian T3 taus inside T star of S3. And these are monotone Lagrangians. Okay? We should say monotone Lagrangians. And again, the monotonicity constant is going to depend on the area that the loop bounds on the base. Okay?
This is specific to 3 dimensions.
Yeah. So I mean,
Not yours, but
this.
Yeah.
Yeah. I mean, there's similar things you can do in higher dimensions, like in I think what. So if you did, for instance, T star of S5. Then you would get Lagrangians that are S1 cross S2 cross S2. Okay? And this you can also do in higher dimensions. You're always going to get S1 times Sn minus 1. Okay? So yeah. So in even dimensions, you always have a one-parameter family of Lagrangians, and in odd dimensions, you always have these two one-parameter families of Lagrangians that don't have the same topology. All right. Any other questions? Yeah.
So you get the monodrome to be 1. I mean, this is just like some fact. Like when you pick a section of like, sphere.
So you can. Let me just say you can arrange things so that this happens. It doesn't necessarily need to happen. Like maybe like if you're not very careful, then you get a monodromy that's like a Hamiltonian isotopy or something. But you can fix your you can make your choices in such a way that these monodromies are actually the identity. Shield, do you agree?
Yeah,
Okay.
no, I was just going to say, in this case, up to Hamiltonian isotopy, this is a composition of 2 Dane twists because you're going around 2 critical points.
Right.
And a double Dane twist is, on the 0 section, it's 2 antipodal maps up to some isotopy, which is just identity.
How do you know it's exact?
Sorry, it's not these guys. They're not exact. They're monotone.
In this case, you can completely
So you can actually exhibit all the disks that they bound.
Don't you want them to be exact?
No. I'm interested in studying monotone Lagrangians in T star of S3. Okay, that's my goal. Okay, so the theorem that I want to talk about is saying the following. So here, before I state that, what we have, the output of this discussion is that now we have this one-parameter family of Lagrangian monotone Lagrangian S1 times S2s, and we have this other one-parameter family of Lagrangian T3s, monotone, in T star of S3. Again, we have a one-parameter family by letting this the area that gamma bounds increase. Okay. So the theorem I want to state is saying that so if L is a closed, I need some assumptions to make the Floer theory work. So I need it to be closed, orientable, spin, and monotone. Okay, long list of adjectives, such that, well, and I want, as I said, I don't really want to go into some of the technicalities, but we want to do Floer theory with these Lagrangians, so maybe it's useful sometimes to equip them with some additional structures, like what people call bounding cochains or unitary local systems. So let me say maybe equipped with bounding cochains or unitary local systems. So I have these Lagrangians such that, maybe equipped with this additional structure, their Floer theory, their Floer homology can be defined and is not 0. Okay? Then what happens is that the conclusion is that then either, if I take one of these Lagrangians, then either it has non-trivial Floer homology with the 0 section S3, which is exact, or it has non-trivial Floer homology with one of these 3 tori. Okay? Actually, I didn't really point it out, but I should have. If you have an exact Lagrangian, then it's monotone with tau equals 0. Okay. Should have said so. L exact means monotone with tau equals 0. So this class of monotone Lagrangians includes exact Lagrangians. Okay, so then either the Floer homology of L with the 0 section is not 0, or the Floer homology of one of these tori with L is not 0 for some positive tau. Okay, so the morally what this is saying is that from a Floer theoretic point of view, anything that's non-trivial, any Lagrangian that's non-trivial, any monotone Lagrangian that's non-trivial, must have non-trivial Floer homology with either S3, the zero section, or one of these tori, T3, for some monotonicity constant tau. Okay? And so
is this tau just the monotonicity constant of L?
I don't know how to prove that in general. Yeah, but that's something I would very much like to know. So in particular, sorry, yeah.
I was just going to ask whether, I mean, in particular, is L split generated by this collection?
Yeah. So what we're going to see is that if you take the compact monotone Fukaya category, it's generated by S3s and these guys. That's how you're going to prove this. Yeah, so thanks for the spoiler.
I just want to make sure, just to sort of put those two together, I should be thinking of these two are sort of shrinking down to.
Yeah, so actually these guys.
It's sort of one family.
Yeah, so yeah, what's happening is that, so I would have drawn a similar picture for the tori here. So what's happening is that when gamma is converging to this segment here, it's actually converging to two copies of the segment. So the tori are actually to be thought of as converging to two copies of the zero section. Okay? All right. So actually, this is, so in particular, so this is an immediate consequence that because it's the Floer homology is non-trivial either with S3 or with one of these guys, L is non-displaceable from either S3 or that guy. Okay, so if you don't really like Floer theory and you want just a symplectic statement with no reference to Floer theory, you can say that if you have a Lagrangian, well, I guess you need a Floer theoretic assumption that it's the Floer theory of the Lagrangian is non-trivial. If the Floer theory of the Lagrangian is non-trivial, then it's either non-displaceable from the zero section or from one of these tori. Okay, so this is trying to say that these tori are in some sense, these tori with the zero section are in some sense all the relevant monotone Lagrangian tori in T star of S3. Okay, and so let me just make a very quick remark about that. So this is this paper. What this paper is doing is this paper of Chan Pomerleanu Wede is it's studying in some sense mirror symmetry for T star of S3. They would call it something else maybe, but you can think of that paper as studying mirror symmetry for T star of S3. And what they do is, if you're familiar with that, they construct an SYZ fibration on T star of S3 minus some hypersurface, and they use this SYZ fibration to construct a mirror, compute a superpotential, and then as it turns out, if you go through that calculation and you look at that superpotential and you take the critical locus of that superpotential, you'll find that the critical locus is going to be precisely a complex affine line. So you have a one-parameter family of non-trivial. This is suggesting that you should have a one-parameter family of non-trivial Lagrangians, and we can think of this family, the zero section, and then the one-parameter family of tori as giving us this one-parameter family of Lagrangians. Okay. This is also another quick comment is that we expect this will be just too vague, but so because we have this picture that the tori are in some sense converging to two copies of the zero section, one could say that these tori are in some sense going to give us a deformation of two copies of the zero section in the Fukaya category. And so we haven't yet figured out all the details, but it seems to play well with this notion that Paul Seidel has studied of abstract analogs of flux. So you see, we have here this S3. So we have this. If you have the zero section on a cotangent bundle, if you take a cohomology class of degree 1, then you could take a dual symplectic vector field and deform the zero section in the direction of that one form. This would be a flux deformation of the zero section. Here, what seems to be happening is that we have a deformation not of the zero section, S3 doesn't happen to have algebra 1. It has algebra 3, and it seems like the generator of algebra 3 is giving us a deformation of the zero section, but of 2 copies of the zero section into this one parameter family of Lagrangians. Okay, so this is also maybe a nice picture to have in mind. All right, this is the statement, and what I want to do with the rest of the time is try to give you an idea of how we can actually conclude this. And the idea is really what Chill was already asking. We're going to argue that these 2 objects, S3 and this one parameter family, so not 2 objects, the one parameter family of tori and the S3 are going to, in some sense, generate the Fukaya category where those Lagrangians L live. Okay, that's going to be the upshot.
Can you replace S3 tau by S1 times S2 tau?
Yeah, you can. There's a little detail that we have. There's a little annoying thing about that we haven't yet figured out. So I would rather just state it for T3 right now, but it's certainly true. And also, one thing that we can say is, well, what if L is this guy, S1 times S2 tau? Then you can conclude from what we know that this guy is non-displaceable from the T3 tau with the same tau. Okay, that's a good point. So if L is S1 times S2 tau, then the Floer homology with the same tau torus is non-zero. Okay. All right. So yes.
So is the in the Morse-Lefschetz vibration is the preimage of the arc still the zero section, or is it something else?
It is.
Yeah.
It is. Yeah. But then, yeah, what's going to happen is that yeah, it is.
You have to say what you mean by preimage of the arc. Oh yeah.
A lift. Yeah.
Yeah.
Yes, yeah. Well, yeah. Yeah. I can say more, but maybe let me not say more at this point. So yeah.
So like if L is exact or like the monotonicity constant is 0, do you know if it has non-trivial Floer homology with S3? Because that seems to be.
Well, that is true. That was known earlier. That's something I guess you can attribute to Fukaya, Seidel, Smith, or other people. Yeah. Okay. All right. So let me try to talk a little bit about the idea of the proof. So we have. So we're going to need to talk about the monotone wrapped Fukaya category that I'm going to denote by script W. And so it's going to be a category. If you're familiar with the Fukaya category, that's great. If you're familiar with the usual wrapped Fukaya category, it's even greater. The idea is just that we have a category whose objects, we have a category W. The objects are, if you want, if you allow me to be a little bit sloppy, let me just say that objects are Lagrangians as in the hypotheses of the theorem, closed, orientable, spin, and monotone, possibly equipped with additional data, bounding cochains and local systems. I don't require that they have non-trivial Floer homology to start with. So L closed, yeah. As in the statement.
Why do you say possibly or maybe there?
Possibly what?
Why do you say possibly? So why do you put this? So you write maybe there. What does it mean? So it makes the statement clear.
Oh, I'm sorry. So what I mean by that is that there are some Lagrangians for which you can define the Floer homology just given the Lagrangian, but there are some other Lagrangians for which you actually need some additional data to make sense of the Floer theory. Maybe when you try to define the Floer complex in the most natural way, d squared is not equal to 0. And then you need, but there's some way of correcting that if it's what's called like a weakly unobstructed, yeah, right? So that's, this bounding cochain is a way of trying to make a differential that's a Floer complex that doesn't have differential squared to 0 into one that does. Okay, so people have studied some of this additional data that you can put on a Lagrangian so that you can actually make sense of its Floer theory.
So the additional data are also carried over the conclusion into the conclusion, right?
Yeah, here, yeah, the additional data should be here. Okay, the non-displaceability statement doesn't care about the additional data. Okay.
So the choice of the bounding constraints matter or not?
Yes.
So you have
So
to
I mean,
make-
so maybe you find a Lagrangian such that you need to choose some clever bounding cochain for it to have non-trivial Floer homology with one of these tori. But then, no matter how clever you were, the statement that you get in the end is that the Lagrangian you started with is non-displaceable from that torus. That statement, that non-displaceability statement, doesn't care about this additional data. That's why I'm not emphasizing that much on this. Okay. All right. So so let me say L is as in the statement. Also, as Umut was asking, why call this wrapped if it only has closed Lagrangians? Let me also put in by hand one non-compact Lagrangian, the cotangent fiber, or L equals the cotangent fiber at some point. Let me denote this by F. Okay, so this is this is a non-compact Lagrangian. So my objects are Lagrangians. The morphisms are, as usual in Fukaya categories, Floer cochain spaces between two objects. Okay, so this is think of this as Floer cochain. So Floer homology. If you have two Lagrangians, then you can sometimes define their Floer homology, which is the homology of a chain complex that's generated by the intersections of the two Lagrangians. If the Lagrangians are infinite, they're not. If the Lagrangians are not closed, like if you have a cotangent fiber, then it's a little bit subtle. It's a little bit delicate how to set this up. You need to say what happens at infinity to these Lagrangians, and we do this by we do this in the framework of what's called wrapped Floer homology. Doesn't the details don't really matter much at this point. If you're familiar with Lagrangian Floer theory, when either L or L prime are compact, then are closed, then you can think of CW as just the usual Floer chain complex. Okay. Okay, and then this is actually not a category in the strict sense. It's what's called an infinity category. So there's going to be higher compositions counting J-holomorphic polygons. So for instance, if you have three Lagrangians, L0, L1, L2, and you count pseudo-holomorphic polygons with boundary on the Lagrangians like this, then these counts define a map mu2 from CW star of from CW star of L1 with L2, CW star of L0, L1 into CW star of L0, L2. Okay, that maybe if you're not very familiar with this, the orders of the inputs here in these Floer complexes are not too intuitive, but this is just a convention that makes things work. All right, so this is the wrapped Fukaya category. Well, this modulo some details, and what I want to say is that we're going to use, this is something maybe a little bit more technical than I should say. But if you're wondering, we use coefficients in the Novikov field over the complex numbers. We actually need the complex numbers. We need zero characteristic, as it turns out. So if you haven't seen this, then let me call it F. Sometimes this is denoted by lambda, but later on I want polynomial algebras in F, and I don't want to confuse that with exterior algebras. So F is just a formal power series field of the form so AI t to the lambda I such that the limit as I goes to infinity of lambda I is infinity, and the AI are, so I should say the lambda I are real numbers and the AI are complex numbers. Okay? It's a field of formal power series. The coefficients are in C. The exponents, instead of just being integers, are any real numbers. There's this condition that the real numbers go to infinity. The reason I'm writing this is that this map here has what's called a valuation, and I'm going to need that valuation from the field to R. And what it does is it takes, if I call this guy A, if I call this element in the Novikov field by A, it takes A to the min of the lambda i's such that AI is non-zero. Okay? So put differently, if you think of these lambda i's as real numbers that are actually increasing, strictly increasing, then the valuation is the smallest of these lambda i's. Okay? It's just a quantity that you can associate to an element in this Novikov field, the lowest coefficient, the power of the lowest coefficient. So, all right. Sorry? I want the complex numbers, yeah.
Not rational numbers, real numbers.
Well, so I need, you could take the algebraic closure of the rationals. I need an algebraically closed field of characteristic 0
Okay.
for some reason that I can talk about later. So,
So that you're going to allow unitary local systems.
I'm going to allow, sorry?
Since you're using unitary local systems, you better use complex numbers or something very close.
I mean, here by unitary, I just mean that I'm going to use like positive, like non-negative valuations. Yeah, I guess. Okay. Yeah. I mean, the exponents are all real, are always real. Okay. So so then I want to say, so now I have a category that I've kind of defined, okay? And there's this result of Mohammed Abouzaid that says that a cotangent fiber, if you take this object here that we added in, this non-compact Lagrangian, the cotangent fiber, that object actually generates the category. So Mohammed proved this in the context of exact Fukaya categories, where the objects are just exact Lagrangians, or maybe Lagrangians that are non-closed. But you can adapt his argument to there's like also work of Nick Sheridan's and of Ritter and Ivan Smith that are useful to try to translate that argument to an argument that also allows for monotone Lagrangians. So let me just state that F, the cotangent fiber, there's beginning to be a lot of things called F, right? F is the cotangent fiber, and F with two legs is the Novikov field, okay? Who knows what lowercase f will be? So F generates W I'm not going to tell you what this means. Let me just say that this implies that the Floer homology of a Lagrangian with itself is non-zero if and only if its Floer homology with the fiber is non-zero. Okay, this is one way you can think of generation. Okay, there's better ways of saying what generation means, but in some sense, just this property means that implies that in some algebraic sense, in some possibly complicated way, you can obtain in the Fukaya category any object as by some complicated procedure starting only with the zero section. Okay, and doing some algebra with the zero section. So not the zero section, the cotangent fiber. Because this cotangent fiber is very important, as it turns out, we can define a certain functor. So now, instead of just instead of thinking as objects, instead of thinking of our objects in the Fukaya category as Lagrangians inside this cotangent bundle, from a very geometric point of view, I'm going to think of them. I'm going to use the fact that the cotangent fiber is so important to think of these objects more algebraically by mapping the Fukaya category to a category of modules. So define this functor. Let's pretend this is a script y for Yoneda from this monotone Fukaya category into a category of modules over A, where A is the morphism space for the fiber. Okay, so now I look at the Floer homology, the Floer cochain complex of the fiber with itself. This, as it turns out, because I'm starting with an A infinity category, this is not really an algebra. It's what's called an A infinity algebra. And then I have a functor from I'm going to have a functor from the rat Fukaya category to a category of A infinity modules over an A infinity algebra. And I'm not really going into the details of what that means. For one, because I don't have time. For two, because one of the upshots of this discussion is going to be that for this, at least for the case of T star of S3, things are so simple that this category of A infinity modules over an A infinity algebra is actually equivalent to the cohomology category. You can start with an A infinity module over an A infinity algebra. You can take the cohomology of the algebra. You just get an algebra, maybe graded. And you take the module, you take the cohomology, you get a module over this algebra, okay, in the usual sense that you learned in algebra, in an algebra class in graduate school at some point. And this category is going to be equivalent to that. So you can think of this as really just a category of modules in the simplest possible sense. So where this is this, mod A is a category of A infinity modules over the A infinity algebra A. And the last piece I haven't told you, the most important is what is this functor, right? So the Yoneda map takes, the Yoneda functor takes a Lagrangian and maps it to a module over the fiber. So what you do is you just take CF star of the fiber with the Lagrangian, okay? So if you look at that picture there, and you take, so give me just 1 second. So if you call this the fiber, and this the Lagrangian, then that operation there, this mu2, if you think about it, gives me a map from CF star, I hope I'm getting the orders right, CF star of F with L, tensor CF star of, sorry. Same picture, L, F, F. We get a mu2 from CF CW star of F with L, tensor CF star of L with L, to CW star of F with L. Okay, so this really looks like an action of this algebra on this module. Okay, and actually you need higher mu's to define an A infinity module, but so if you start with this cotangent fiber F, then you can use it to map the Fukaya category to a category of modules over F. Okay, and one way, if this was not abstract enough, one way of interpreting this theorem I should have attributed to Abouzaid is that
there should be F and F, right? Because you want the self.
Here?
No.
Oh, yeah, thank you. Thank you very much. Yeah, this was a typo. Sorry. I'm glad I didn't write W. At least I didn't write W. Okay, I hope this is correct now. So, so one way of thinking about Mohammed's generation criterion is that this functor that takes a Lagrangian and spits out Floer cochains of that Lagrangian with the special guy that generates actually does not lose any information. This is what's called a cohomologically fully faithful functor. Okay, so Y is a cohomologically fully faithful functor, which is a terrible thing to say, but you can think of it as just saying that if you want to study the Fukaya category, the wrapped Fukaya category, you don't actually have to if you have an alternative way of studying this category of modules over A. Okay, and now you can actually do algebra because A is an explicit algebra, and you can try to study this algebra problem of classifying modules over that A infinity algebra. Okay, so so the idea, let me say, sorry. So in the statement, I only care about closed Lagrangians. I don't really care. The statement doesn't say anything about the fiber. The fiber was an auxiliary Lagrangian that generates in that sense. So I take F inside W that just not containing the fiber. Okay, I have a subcategory of the Fukaya, of the wrapped Fukaya category. This is what people might want to call the Fukaya category, the compact Fukaya category. The objects are just closed Lagrangians, no fiber. And then I have that this Yoneda map, this Yoneda map Y, actually takes F, restricts to a map that lands in the category of what's called proper modules over A. So here's another piece of terminology. A module is proper, a module being proper just means that its Floer homology is finite dimensional. This is just saying that if you have a compact Lagrangian, its Floer homology is finite dimensional. Okay, but if you think about it, like if you want to study modules over an algebra, it's a big improvement in the studying of that to be able to assume that your modules are finite dimensional rather than allowing a zoo of infinite dimensional modules. Okay, so these here are proper modules. Okay, these guys are proper modules, so they're finite cohomology. The cohomology is finite dimensional. That's what the module being proper means. And So now formality and classification of modules. Let me abbreviate this. Let me actually bundle 3 and 4 together. Let me just make a statement at this point. What we prove is that the category mod of proper modules over A, okay? So the target of this functor that starts with closed Lagrangians, compact Lagrangians, and associates to them modules over the fiber, okay? This target, the target of this functor, okay? So proper modules over the fiber. This is split generated by what? Well, I'm telling you there's some special Lagrangians. I'm going to prove that there's some special, in a non-technical sense, Lagrangians S3 and T3 tau, okay? And so what one way of formalizing what Shiel was suggesting earlier is that this category of proper modules is generated by the images of these guys under the Yoneda functor, okay? By y of S3, actually, let me say S3 comma A, and so a collection S3A, where A, yeah, thank you. So A is some element in the Novikov field. So the way you can think about this A is, I'm telling you that we may have to equip Lagrangians with certain additional structures, okay? So there is a way of using the 3 cohomology class, a generator of 3 cohomology in S3. Okay, we have a degree 3 cohomology class in S3. We can multiply that by an element in the Novikov field, okay? As it turns out, that gives me a bounding cochain on S3. So I want to think of the S3, the zero section, as not just giving me one of these generators, but it's going to give me an infinite family of generators, one for each element in the Novikov field, okay? So actually, I need a constraint. I need the valuation to be non-negative, So, but anyway, let me just leave it like this at this point. So
That you choose infinitely many bounding cochains?
Yes. Yeah, but yeah. So it sounds a little bit unreasonable, but you see, if you start with some Lagrangian, and this Lagrangian, as it turns out, is has non-trivial Floer homology with S3 with some random bounding cochain like this one, you can conclude that the Lagrangian is non-displaceable from the S3 without reference to the bounding cochain. Okay. So again, we're going to think of these. We're going to think of the fact that we have this zoo of bounding cochains as a good thing. It enables us to compare more things with the zero section. So we have these objects such that, maybe let me write here, the valuation of A.
Do you really require that?
What? That the valuation is non-negative?
Non-negative. You don't require it to be 0.
No.
The valuations of the things you'll use for those values will be 0. For the
Yeah.
tori will be 0.
They will actually be negative, as it turns out. So let me put it like this. So I need some modules associated to Lagrangians. I have a one parameter. I have here a one parameter family of modules associated to the S3, and then I also need the Yoneda image of T3 tau. Well, I've equipped the S3 with the bounding cochain. Now, just to be different, I'm going to equip the tori with a unitary local system. Okay, and this is unitary, but the tau is positive. Okay, so you can actually think of this T3 with the unitary local system as just this family. You can kind of think of that as just some fixed T3 with some equipped with a non-unitary local system of negative valuation.
So this is how you
This is how you construct the line. Yeah. This is. I'm trying to illustrate. I'm trying to give more details into this picture that Mohammed drew at some weeks ago when talking about non-Archimedean geometry. He was talking about a line that you associate a Berkovich line that you associate with a non-Archimedean line that you associate with T star of S3. I'm telling you that you have the unit disk that's given by bounding cochains on the zero section, and then the complement of the unit disk is given by this one parameter family of tori.
I think he only talked about the unit disk.
Yeah.
But you talked about the line, like that's from the mirror symmetry.
Right, right. Yes, yes. Yeah. Yeah. Okay. So, any other questions? So let me just say, this theorem, as it turns out, so if you unwind what this split generation means, what this split generation implies, well, the fact that the fiber generated the Fukaya, we saw earlier, the fact that the fiber generates the Rat-Fukaya category implies that non-trivial Floer homology means non-trivial Floer homology with the fiber. Now, the fact that this, as it turns out, the fact that the modules that you associate to the zero section and this one parameter family of tori, the fact that these guys generate the target of this functor also implies, by just similar argument, that the objects that the objects that you start with, these S3 and tori equipped with additional structure, generate the F. And that implies that if you have something in F with non-trivial Floer homology, then it must have non-trivial Floer homology with at least one of these two types of objects. And that's exactly what the theorem is saying. Okay? So, this is really, you can think of this as just some restatement of the theorem in some sense. And then what I should have said if I had time, is how do you actually go over the proof of the fact that these guys split generate, and that.
Maybe you have 8 minutes if you want.
I have what?
8 more minutes if you want.
8 more minutes?
Yeah.
Rip? Oh. Okay. Okay. Thank. Is this on the deal, or am I going to upset people by taking these?
Yeah, it's okay.
All right, I'll take it. Okay. So. Let me, so now I have to think about what I want to say. Did my piece of paper fall there? Oh, why? Oh, no, it's there. Okay. Sorry.